Recording in progress.
So it's now sharp 8 here in mid-European time. Or should we maybe wait a few more minutes in case people are arriving exactly?
Yeah, okay, we can wait a couple of minutes. You tell me when you want me to start.
Yes, yeah, perfect. Let's wait like 2 minutes, let's say. Okay, so I think it's time to start. Welcome to the last session of today in the seminar Laser Physics. We have 3 speakers in the program for the last session. I think that I see now 2 of the speakers online. Let's hope that the third one also appears during the session. The session will be opened by Francesco Papov, who comes from Glasgow. And the stage is yours, Francesco.
Okay, thank you very much. So I'm from the University of Strathclyde in Glasgow, and I will speak about quantum correlation and laser threshold. This is an outline of the talk. I will be first introducing the main properties of quantum dot nanolaser. Then we'll move on to the way we describe light-matter interaction and dissipation, and from that how we can derive equation of motion for expectation values. I'll be looking first of all at the semi-classical theory, and we'll look at the prediction of this semi-classical theory in terms of laser thresholds and how that can be identified in terms of the first order coherence. Then I will introduce a quantum correction and see how they affect the laser threshold. And then if I have time, I also mention something about the second order coherence and anti-bunching. The co-authors of this work are Marc Anthony Caro, Giampaolo D'Alessandro, Gianluca Oppo, and Gianluca Lippi. So here is 2 nice pictures from a paper that was published a few years ago from Kreinberg and others of a nanopillar quantum dots laser. And the key features of not just this type of nano laser, but generally speaking of all nano lasers, are that they are extremely miniaturized. They are the smallest laser we have at the moment. They do have minimal energy requirement. They do have an extremely low number of field modes that are coupled to the emitters. And for some of them, at least, there are also a relatively low number of emitters. So that means essentially that we are dealing with the systems that are well within the realm of quantum mechanics, and in particular of quantum cavity electrodynamics. So very quickly, we will describe this in terms of a tonal Hamiltonian that is made up by 3 different bits. Now, if you're not very familiar with quantum mechanics, it doesn't matter. What really is important is that one of the 3 bits is essentially the energy associated to the photons inside the cavity, that is electromagnetic energy. The second bit is the energy associated to the charge carriers in the semiconductor. And finally, the most important one is the light-matter interaction. And this is done in terms with the assumption that we can approximate everything in terms of the dipole. That is the most important transition that we consider. And not only that, but we also make the rotating wave approximation. So we only consider processes that on their own conserve the energy, for instance, absorption of a photon and excitation of a charge carrier. What we do not include in this are the Coulomb interaction, which are modeled simply as in terms of a carrier dephasing. And we assume that the internal environment is introducing dissipation through the Born-Markov approximation. So we assume that there are no correlation between the nanolaser and the environment. And the environment dynamics, the bath, is so fast that there are no memory effects. So these are the standard approximation that we make. And we work in the Heisenberg picture, which means that we are able to derive equation of motions that are of this form. Okay, so the first part here, this is the expectation value of any operator A, and the first part is the conservative part that comes from the Heisenberg equation. It's just the expectation value of this commutator. And then we have the dissipative part that is done through the Lindblad formalism. And the theory has been developed several years ago, and this is a nice paper when you can find it assumed here. Now, the very key point is that if we do that, we have an infinite hierarchy of equation of this type for all sorts of operators, so they become longer and longer. And at some point, this hierarchy has to be truncated. And in general, the way we do it is we keep only correlations between different operators up to a given number of particles. Further to that, and this is certainly the first things that we really have introduced ourselves, we do consider the time behavior of this operator. I remind you that we are working the Heisenberg picture, so the operators have a time dependence. And we look at essentially how fast they vary in time. So there are fast operators that oscillate that have oscillation of the order of the laser frequency or of the order of twice the laser frequency. And their expectation value of these operators that I use in red or in blue, depending on how fast they oscillate, are normally 0 for incoherent processes. However, there are also other operators that do not have a fast components, and for them, normally the expectation value is 0, also for incoherent processes. So the key parameters that are common to all the models I'm going to introduce in the following are the pump rate for emitters, the decay rate of the polarization, the decay rate of the laser mode, the decay rate into the non-lasing mode, the non-radiative decay rate, and then the decay rate into the lasing mode. And here we have this extremely important parameter that allows us to distinguish what is really a nanolaser from what is a micro laser, because that is the ratio between the decay rate into the laser mode and the total radiative decay. So that when this is 1, we have essentially that all the spontaneous emission goes into a single mode, which is the laser mode. When this is very small, 10 to the minus 6, typically a value for a microscopic laser. And it means that the spontaneous radiation is distributed among a very large manifold of modes. Okay, so the first model I'm going to talk about is the simplest of them all, and this is essentially a semi-classical model. We have two coherent variables, which are the expectation values of field and medium polarization. And we have three incoherent variables, which are the population of the excited state, and then the photon assistant polarization and the number of photons. Now, the photon assistant polarization is nothing else than the expectation value of an absorption of a photon, which is followed, which is happening together with an excitation of an electron. Okay, so the key approximation is that we neglect anything else that has a larger number of operators. So no higher numbers of operators are included in the equation for the expectation values. And also we not include a correlation between fermions. And this is the most important one, and that is what characterizes this as a semi-classical approximation. We assume that the expectation value of the product of the absorption of a photon times an electron in the upper states can be written as the product of the two expectation values. What that means is that we are neglecting quantum correlation between the field and the population. So this is the semi-classical approximation. Okay, the main features are actually that we find analytically for this type of semi-classical model two solutions. One in which these coherent variables are zero, and the other in which these two coherent variables are different from zero. And this is what corresponds to the classical continuous wave lasing. So I'm going to present side by side the results of two slightly different models of emitters. One in which, in both cases, we have only two energy levels, but in the first case, we only have one electron that can go up or down. And in the other case, there are actually two electrons. So if the spins are like in these figures, then the electron in the excited state can decay. But if the spin of the electron in the lower energy level is in the other way around, then for the Pauli principle, this decay is forbidden. So that means that in a situation like that, the probability of transition depends on what is in the lower level, and that makes the lifetime in the excited state slightly higher. So that means that, we will see there is a lower threshold, but the difference between these two models is actually very small. So starting from the top, we have what we see is that there are what are presented. The dashed line corresponds to a multi-electron system, the continuous line to the single electron. And what we see is that we have for the curve corresponding to 21 quantum dots and 40 quantum dots, we have the excitation of a continuous coherent field that corresponds to a continuous self-sustained stimulated emission. So this happened earlier on for n equal 40, which is in green. A little bit later, you need to pump harder for n equal to 21, but there is absolutely no lasing radiation coming out of a laser with only 20 quantum dots associated to that. Looking now at the second panel in this figure, at the center, the one marked B, what we are showing is the correlation between absorption and emission processes. And what we see is that in correspondence to the appearance of continuous stimulated radiation, we have these discontinuities. So before there is this appearance of continuous stimulated radiation, we see an increase in the correlation between between absorption and emission process, and then a sharp turn towards the lower part of the figure. And that is exactly the same. And this indicates that actually in nanolaser at least, but we'll see also to some extent in micro laser, it's just happening on a much faster, on a much smaller scale. The lasing is at the end of a build-up of coherence that is affecting the other solution. If we now look, and that is the last panel marked C, how where the thresholds are with respect to the standard characteristics curve, in which on the vertical axis we have the number of photons or intensity of radiation, then we see that for this nanolaser, the transition to lasing happens after the inflection point. So happens towards the knee of these curves for the lasers which do actually end up lasing, while obviously it doesn't happen at all for the laser which has only 20 quantum dots. Okay, now moving on to the dependence on this threshold with respect to the parameter beta and the number of photons, we see essentially, and I'm showing curves for 21, 40, 100, and 1000 quantum dots. First of all, we see that if you increase the number of quantum dots inside the nanolaser, then the threshold goes down, and that is an effect that is relatively well known. The other thing that we see is that as we move from microscopic laser, which are at this end for small value of the beta parameters, toward the nano laser, which are at this end towards beta equal to 1, we have first a very rapid decay, and then there is a gradual saturation. In terms of beta, looking now at what happens for looking at the lower panel, what we see is that for beta equal to 1, so the case that has been for a long time called laser without inversion, because the 2 points corresponding to the threshold can be either on the knee of the characteristic curves or right in the middle for value of beta corresponding to a microscopic laser. So we see quite clearly in these figures the transition from microscopic to nanolasers in terms of where the laser is. Now, how do we identify that in an experiment? And I think we have, and the first order coherence is the most direct way of observing these effects. The first order coherence corresponds to the visibility of fringes, and here I'm comparing the results of this work, Temple et al., published in 2011. And here, what we have is visibility fringes in two different cases with two different delay, which correspond to two different shift in the length of the arms of an interferometer. And here we have the characteristics curves with the intensity as a function of the pump. And as you can see, corresponding to this point, starting from this, which is towards the low part of the intensity, we have that as the intensity moves up on these characteristics, the coherence times improves and becomes quite high towards the upper part of the curves, and again, well above the inflection points in the intensity curve. And we have the exact same situation in our theory. So our theory here shows exactly the same effect with this point here, which is well above the inflection point in the intensity curve, showing a very good coherence. In terms of the threshold, the theoretical threshold, We know that this point is 70% below, is at 70% of the threshold, so the threshold hasn't been reached yet, but it is clear that the threshold is going to be above the inflection points. Okay, so in terms of how one can imagine to be able to detect this threshold experimentally, expanding from the early experimental works, we have suggested a possibility here. So you can look at, you can fix the difference between the paths of the two arms of the interferometer, and then increase the value of the pump. And in this, and what you see, and these are two figures, the first one reproduces what you could see for n equal 40 for 40 quantum dots. You see, depending on beta, you can have a slow, a gradual increase in the visibility of the fringes. And then you have, in our theory, you reach 1, and then the coherence stay at 1. This is because this is a semi-classical curve theory. Sorry, in an experiment, you will not have 1, but you still see very clearly a difference in the way these curves behave before and after the threshold. Now, as the beta decreases, so as you move from a nano laser towards a macroscopic laser, you see again what we have seen in the theoretical curves. But you could notice here in these curves that can be directly measured. You can see that the length of the transition becomes smaller and smaller. And here, for the smallest value, which is 3.5 times 10 to the minus 6, this is a macroscopic laser. You see that the transition is essentially almost discontinuous, essentially almost vertical, and that is what you would expect in a macroscopic laser. If you increase the number of quantum dots inside the cavity, the situation remains essentially the same from a qualitative point of view. The only thing is that, as we have seen in the previous slides, then all the thresholds moved at lower values of the pump. But essentially, you do see what these two curves shows is that there is a possibility to detect experimentally a threshold which corresponds to the laser becoming a continuous wave laser with self-sustained spontaneous emission. Sorry, self-sustained stimulated emission. Okay, so in terms of the main achievement of this theory, which is very simple, we have an equation for the population inversion and also corresponding at threshold, and corresponding to that something for the an equation for the pump, the value of the pump. We do have that there is a critical number of quantum dots. We can identify the critical number of quantum dots below which we do not have lasing. And most importantly, and that is due to the fact that we have kept those coherent variables that in many other treatments are discarded, we have the possibility of identifying the central frequency of the laser line. So this, when you have continuous self-sustained stimulated emission, you have a laser line which is centered somewhere, and this is where it is centered in this theory. Okay, now I want to move on beyond the semi-classical theory and look at the effect of quantum correlation. And in order to do that, I need to introduce other variables which are shown here. We have the expectation for values of two photon processes and their correlation. We have photon emission, absorption, and electric excitation or de-excitation. And then we have a correlation between different pairs of emitters, the correlation between polarization, population, or polarization and populations. But the key point is these are between different types of emitters. Now, correlation between different emitters are the effects that lead to superradiance. And when superradiance effects are negligible, you can approximate this expectation value in terms of the product of the expectation values of a single emitter. Okay, so the key things that is in common to all quantum models, we will see there are differences depending on how you treat the presence of superfluorescence. The two key features that are not in the semi-classical theories are shown here. First of all, now the coherent solution does not appear from a zero value, does not grow from zero, but start all of a sudden from a finite value. And there are two possible lasing solutions. One in blue, the continuous blue line, that is the stable one that you do observe in a real experiment. The one with the red dashed line on top is actually unstable. That is the sort of barrier which would prevent the excitation of the lasing solution. That tells you that in order to reach lasing, you need to provide to this system a finite initial perturbation, a final burst of coherent photons, which needs to be higher. This initial burst needs to be higher in terms of number of field intensity than this red dashed line. And that is the first major point. And this is common to all quantum models. As soon as you introduce quantum correction, you do have this. And the second that is also very important is that while with the semi-classical theory, there was this rather unphysical situation in which the coherence is identically one, corresponding to an infinitesimal line width. In this case, we see that even for the lasing solution, there is a small decay of the coherence as you increase the delay between the two arms of the interferometer, which gives you the possibility of calculating exactly the line width. Okay, so this is a summary of the main points. The others are that the non-lasing solution exists and is stable for all values of the control parameter. However, the stability windows become extremely small as the pump increases. And the final point is that once stable lasing is achieved, it can be sustained by an incoherent pump. So this is all these models do not require coherent pumping. You might need a coherent pump just to jump above this barrier here, but once you are there, an incoherent pump will be able to sustain a coherent laser solutions. Okay, now the thing I want to discuss now is the effect of superfluorescence. So the two fermions correlation between different quantum dots. Okay, so here we have 25 quantum dots on the left, 100 at the center, and 500 in the right. And I show three different colors. In red, we have the semi-classical model. In green, we have the model in which the correlation has been neglected, but there are other quantum effects such as the correlation between field and polarization. And you see that there is always this, the lasing starts at the finite value of B, but then there isn't much difference between this, the green curve and the red curve for 25, and that becomes even less visible as you increase the number of emitters. However, the blue curves corresponds to a case in which superfluorescent effects are present, remain always distinct from the semi-classical case, not only, but as you increase the number of quantum dots, actually the difference becomes even more striking. So this shows that if superfluorescence is present, it would sort of fight against the establishment of lasing. However, this is also an effect, and sorry, maybe before I move on, let me say that this is something that would, this situation here is a situation that corresponds to quantum dots or emitters that are in an absolutely uniform environment, because the decay rate that is considered in this model for two-particle correlations is simply twice the decay rate of the polarization of the photon, which comes from modeling the backgrounds in terms of an absolutely uniform background. So this would be essentially a model that is more suitable to a gas, to a collection of atoms in gas, rather than a collection of emitters in a dense medium. So if instead you assume that because there is a non-uniform medium, that there is something going on between different emitters, that the decay rate of the two particles correlations is even only 5% higher than the decay rate of the polarization of a single emitter, then you see that this effect in the blue curve now becomes much closer to the other two, even for 25, and already from 100 becomes essentially indistinguishable. You do always see a difference in the point at which the lasing starts, so that the threshold remains distinct, but apart from that, everything else becomes identical. Okay, so just to summarize, in terms of lasing, we've seen that the semi-classical model provides lower bounds to the pump threshold of coherent solution and critical number of quantum dots. In all models, the transition to lasing is characterized by an increasing coherence of the non-lasing solution, even without continuous stimulated emission. Two-particle fermion correlation increase the thresholds, making more difficult to have a constant population inversion. However, the effect of two-fermion correlation is strongly reduced by a small increase in the decay rate of the two-fermion correlation with respect to the standard polarization. Okay, I will then very quickly move on to something else, which is anti-bunching. If you look at the second order correlation, which is given here, you see that the second order, depending on the value of the second order correlation, you can identify different statistical regimes. This and the most interesting case is when this correlation here, G2, is less than 1. This is the so-called anti-bunching, which is a quantum corresponds to a quantum statistic that doesn't have a classical correspondence. Now, and the very interesting thing is that if you look at the ratio between delta n and n, so you look at essentially at the intensity noise, you see that this is given by this formula here, which means that the photon number noise is minimized by G2. So the smaller you can make G2, the less is the photon noise. And now these are effects that have been seen also by other people. In the first paper I mentioned in the 2017, they had experimental evidence of this. You can see that in quantum dot nanolaser, you have regimes in which the G2 can go below 1. So this corresponds, the part in yellow in these panels corresponds to a situation in which we have anti-bunching. And what you can see is that actually the anti-bunching, looking at this value here compared to this value there, the anti-bunching is actually stronger if you have a lower number of emitters. Okay, which is quite understandable because the more emitters you are, the more classical the systems tend to be. However, this is quickly, these two curves instead show the advantage of having anti-bunching with respect to lasing. These two curves compare a laser and a device operating in anti-bunching with the same number of photons. And as you can see, there is an advantage in terms of the reduction of photon noise. And on the left-hand side, you compare the effect of 1% of fluctuation in the pump on these two devices. And as you can see, the Poissonian would correspond to a laser. And there is a significant advantage, even in presence of pump noise, if you are able to operate in the anti-bunching regime. Okay, so I think I can now move to the conclusion. We have derived nonlinear models of nanolaser, which allow us to investigate transitions from thermal, anti-bunching, and lasing emission. All models show that lasing is impossible, provided that the number of quantum dots is above a critical number. But in all quantum models, lasing can be achieved only if triggered by a finite burst of photons. The threshold we use identifies continuous wave stimulated emission that is established at the end of a coherence build-up. And in terms of open question, there are two that are particularly, I think, interesting, is how strong coupling affects the onset of lasing. Now, having used the rotating wave approximation, I'm able to describe lasing in weak coupling situation. As technological progress allows people to make a smaller and smaller laser, then nanolasers enter into the regime of strong or possibly maybe one day even a very strong coupling, for which other terms will need to be included in the Hamiltonian. And then I think that the multiplicity of solution, the fact that we identified several possible solutions, is in principle recipes that could lead to dynamical instability on very fast time scale, and that is something that will be worth exploring in future. Okay, thank you very much for your attention, and thank you for the invitation. And before I finish, let me tell you that there is a call for complex optics. There will be a special issue of complex optics, and I hope you will be interested in sending papers to this special issue. Thank you very much.
Thank you, Francesco. Excellent talk, very clear. Can we have questions from the audience? We still have like about 3-4 minutes left of the session for first talk. If there's no question at the moment, I have some questions that came across while the talk. Actually, in the end, you touched a bit the topic of strong coupling, and I wanted to ask that what other modifications does it require to include strong coupling in this description than possibly their counter-rotating terms, which are basically only valid for the ultra strong coupling, but just for like strong coupling compared to weak coupling, what modifications?
I think the modifications are, you see, there are other terms here that have been neglected. Essentially, instead of having, you could have B dagger here, a B dagger here, and other terms that are B dagger instead of B. And here, instead of having, you would have B instead of B dagger. Now, neither of those two terms on their own conserves energy, but if you put them together, the energy is conserved. Now, in the strong coupling regimes, they are probably perturbation, but they are important because without them, the symmetry of these Hamiltonian there is a phase invariance in this Hamiltonian. And that is an important symmetry, which is also the symmetries behind the lasing bifurcations. However, if you introduce those two terms, that symmetry is broken. It's probably broken. The effect is negligible, definitely in weak coupling. But as soon as the coupling starts to become bigger, that effect could be big enough to break the symmetry. And breaking the symmetry would certainly change also the type of bifurcation you see. There have been papers done not in nanolaser, but before. I think one of my co-authors was actually involved in one of them. And if you include those terms, if I remember correctly, what happens is that the frequency becomes a function, a nonlinear function of other parameters. This is typically what happens in nonlinear oscillators. The fact that it doesn't happen in lasers is because there is this extra symmetry.
Okay, thank you. Let me check again if we have any questions here. It seems not, so let's thank Francesco again for the talk. And we move on to the next speaker, who is Aris Simos. You are here? Yes.
Yeah.
Hi.
Hi.
Yes, you are free to share the screen now.
Yeah. Give me a moment. This should be it. Super. Can everybody see my screen? I hope so.
Yes, they're there. Okay,
Super.
So the stage is yours.
Yeah, thank you very much, Antti. Hi everybody, my name is Aris Simos. I'm from the group of Stefan Reitzenstein at the Technical University of Berlin. And today I'm going to be talking about the verification of lasing through a line shape anomaly in high beta nanolasers, which has been a work, as you see, of many different groups collaborating, so experimentally, fabrication-wise, and theory-like also. And this has led also to a very nice publication in the previous year, 2022. So without any further ado, let's begin with the motivation of this talk, which are, of course, nanolasers that can pave the future in the engineering of optoelectronic components and photonic devices, which operate in the realm of quantum optics. Why are they so popular? Well, it's because of their ultra small size footprint in terms of volume and mode volume as well. And of course, for the high energy efficiency in terms of low threshold. On the same side, they are also very promising building blocks in applications of quantum nanophotonics and neuromorphic computing. For example, in this example of optical interconnect in a supercomputer, right now the hardware would be VCSELs, and they would be connecting the laser driver and the receiver circuit through an optical fiber. Whereas in the future, this could be done through nanolasers and a waveguide array. And on the other side, regarding neuromorphic computing, you can see here a reservoir computing platform that utilizes a VCSEL array as the hardware platform. And of course, this could be also in the future nanolasers with higher density, of course, of structures on there. Metallic nanolasers that can operate onto plasmonic modes with extraordinary typed optical confinement. So very near to the fundamental wavelength limit and even below, surpassing that. And as you can see throughout the years, there has been a trend beginning in the 1960s with edge-emitting lasers, which were pretty much bulky. And over the years, the lasers have become smaller and smaller in size and also tighter in the sense of optical confinement, arriving then in the year of 2007 to 2010, so to say, where we developed the first metallic and plasmonic nanolasers. What happens through the tight optical confinement is that you have a very highly efficient spontaneous emission coupling in terms of a beta factor, as Francesco also more or less introduced that to us. And in this case, if we reach values near 1, then the following thing happens with the optical and quantum optical properties of the lasers. So in the conventional sense of a laser, so with the beta factor being very small, you can see always a very pronounced kink, which is the lasing undergoing the lasing transition, and you can see a very nice threshold. And at the same time, you can see an abrupt jump in the line width power dependently. But when you go towards values of beta equal to 1, then you can see that this threshold is not very much distinguishable anymore, and there's no abrupt jump. So in this case, you need the quantum optical investigation in terms of G2 measurements, for example, where you can always identify a finite pump power, where you can see that the emission goes from the thermal regime of terms of G2 equal to 2 towards values of G2 equal to 1, which be then Poissonian statistics. So due to this identification of lasing being challenging, this is why we always use, like most of the times we would use quantum optical studies to verify lasing, to validate it. And our question in this sense would be, maybe other unknown lasing indicators. And in fact, what we have identified is that there's a line shape transition from a Lorentzian to a Gaussian profile in the emission spectrum, which is going to be the primary topic in this presentation. So very briefly about the sample and the experimental setup. The nano laser that you can see here under the scanning electron microscope is right now just a pillar that underwent etching. Basically what happens is that we grow with the 3-MOCVD indium gallium arsenide multiple quantum wells on an indium phosphide substrate. Then we deposit a thin layer of aluminum oxide to reduce the optical losses, as you can see here also schematically, and then we cap it with the silver to form the cavity. Then about the experimental setup, what we have two parts mainly. So this is a microphotoluminescent setup where we excite and collect confocally the emission of the nano laser and guide it through some optics into the monochromator, where we can spectrally analyze the signal on the CCD. And alternatively, we can exit the monochromator and guide the light into a fiber-coupled Hanbury, Brown, and Twist setup, which is used to perform the photon autocorrelation measurements and has a resolution of 80 picoseconds. So starting with the first results that are very, very basic and rudimentary for this kind of lasers always is to begin the microphotoluminescence and looking what's happening power dependently there. Well, at low powers, we can see that there's a broad peak arising in telecom wavelengths at around 1440 nanometers. And this is mainly because of the quantum spontaneous emission coupling to the mode. And as we increase the intensity, we can see that this line becomes sharp and, of course, also higher in intensity, much more intense. We use, in this case, a Voigt fit to extract the input-output curve, the full width of maximum, and the coherence time from the spectra, power dependently. And this you can see on the middle and the right graph, that we can see that there's a soft S shape in the input-output curve with a threshold at around 65 kilowatts per centimeter squared. And this is accompanied by a tenfold increase in the coherence time, which is calculated through the full width of maximum of the spectrum. This indicates that this is most probably a high beta lasing, but we're not sure. At the same time, we have a fully quantum optical microscopic theory that reproduces excellently the results. But still, we cannot say for sure that this is a high beta lasing. So for this reason, we went on to the quantum optical measurement part. And in this case, what we would expect, as I said at the beginning, is that the G2 starts at values of 2, and undergoing the lasing transition, you would reach values of G2 equal to 1. But experimentally, this is not always observable, as a lot of people know, because below the threshold, the signal is strongly convolved with the instrument response function due to the coherence time being very low in comparison with the resolution time of the HPT. So in these terms, you get G2 values that are very near to 1 in the thermal regime. And then near the threshold, you would expect you have a mix of thermal and coherent emission with an increased coherence time. So this is where you would expect the maximum of the G2. And this is exactly what we see as well, that beginning at the thermal regime, we have low G2 values. Then around the threshold, we see that there's a more pronounced peak. And then again, going downwards and upwards onto the power, we can see that the G2 decreases and goes to reach the values of G2 equal to 1, which is the Poisson level. And this relates to a coherent emission. So good is that that of course we have validated that more or less in the experiment, but still the lasing transition is very soft. We have the matching theory, but the bunching values are similar due to the low coherence time. So in this sense, what we have done, and also people in the past, is that we apply an extended Siget relation that connects the second order correlation to the first order correlation. And that way, if we also add a parameter R that can also extend this Siget relation to a mixed thermal state, mixed states of light, so to say, not only thermal ones, we can deconvolute these raw values, and then we see that below the threshold we have a deconvoluted value that is very, very near to 2, so 1.99. And as we increase the pump power, we undergo this Leysen transition and we reach the Poisson level of G2 equal to 1 above the threshold. So in this sense, since both the raw and deconvoluted G2 values are theoretically matched, we can now say that we have an unambiguous validation of high beta Leysen. But the only part that I have left right now up to this point out was the discussion about the line shape. And this is, of course, because we saw that something kind of novel happens there. And we wanted also to explain that in a sense, because as I said, we used the FOIG profile because we saw that the fitting wasn't actually matching neither actually not a Lorentzian nor a Gaussian in a sense. So we want to distinguish between the Lorentzian and the Gaussian part, so the both line widths. And in this sense, as you can see here in the power dependent line width of the Lorentzian, which are the red dots, we see that there's this expected line width narrowing when you have the Leysen transition. But near the threshold, we can see that there's a Gaussian part, these black dots arising. And the question was, is it maybe related to the Leysen transition because it's happening at the Leysen threshold? Above the threshold, we can even see that the Gaussian surpasses the Lorentzian. So this is the more pronounced part. And what we did is that we just calculated the shape factor as a weighted sum of those line widths. And this reflects then the line shape transition happening from a pure Lorentzian starting at low powers, which is mu equal to 1, to a more dominating Gaussian, as you can see at the onset at the threshold, which to a dominating Gaussian with a value of mu equal to 0.22. So what we saw is that the microscopic quantum optical model reproduces the Lorentzian, but of course fails to capture the Gaussian part. And of course, we want to know what's the explanation behind that. What is the origin of this Gaussian part? And in this term, every time we work in a fully quantized model, we think about a closed cavity system. But what we developed is a semi-classical model on the basis that you can have eigenmodes extending into free space. And this semi-classical multimode model then utilizes this composite cavity free space system as an open cavity system. And what we can see is that above the threshold, there are nonlinear contributions of the gain medium and frequency locking that leads towards frequency pooling of the different modes towards the central frequency. And this then gives us a profile that's kind of different from a Lorentzian or a pure Gaussian. As you can see here, for example, the black dots, which are the experimental values, can neither be reproduced from a pure Lorentzian or a pure Gaussian, theoretically, but something in between, which is given through this yellowish or mustard-like line here. This is basically the model, and this produces then a FOIG profile, and this matches the experiment very well. And as you can see in the second graph below for the power-dependent full width of maximum behavior, above the threshold, the theoretical lines, which are the dust lines that you can see here, they actually predict that the Gaussian part is going to overtake the Lorentzian, and then this is going to be the more pronounced part of the line width. So the Gaussian part and the light shape transition are reproduced. They are related to the onset of the stimulated emission, and this then serves as a very convenient Leysen indicator in the sense of if you cannot perform the G2 measurements, you can take a look maybe also at the shape factor. And this brings me to the summary of my talk. What we have done basically is that we have quantum optically investigated a high beta indium phosphide based metallic nano laser. We validated, first of all, lasing in the photon autocorrelation measurements. And then we also saw that there's a line shape transition from a Lorentzian to a Gaussian on the onset of the stimulated emission. We related that to the frequency pooling of cavity eigenmodes extending to free space, as you can see here. And that way we can provide now a novel and convenient lasing verification through the shape factor mu, which is calculated through the sum of the line widths. And yeah, last but not least, of course, I want to thank all the fundings that we have get through different organizations and foundations. And of course, thank you for your attention, and I'm open for questions.
Thank you, Aris, for the excellent talk, and thank you for keeping it very much in the time. We have now time for the questions. So go ahead, whoever has a question in mind.
Yes, Gianluca, thank you very much. That's very interesting. I'm trying to understand the more conceptually the origin of what you're saying. I see one phenomenon which I think you are excluding, but I mean, it's the first one that comes to mind. You correct me if I'm wrong. I think you're not really considering seriously the possibility that your quantum dots may have different central frequencies, so in a sort of inhomogeneous broadening, which of course would give some Gaussian contribution, so you would have a Vogt profile that's normal. I would not be too surprised that actually when you bring them strongly into the picture, they would contribute to that. And I'm trying to interpret your statement there of saying that the open cavity will give a Gaussian contribution. That I find it a little more difficult because in general, I mean, a Gaussian contribution comes from the fact that you have independent fluctuations. I'm not sure how the openness, let's just say, of part of the cavity would be opening the door to independent fluctuations. Can you please explain that part?
Yeah, so basically we don't have quantum dots here, we have quantum wells, and we have also investigated what's happening because we were thinking at the same time that this may be relating to the coupling of the quantum wells with different strengths, for example, or different frequencies. And we have actually, this was our first guess that maybe this is what's happening here. But what we have seen is that actually the inverse phenomenon is happening, that you can start from a Gaussian profile, and then you would result in a more pronounced Lorentzian as you increase the power. So this is what more or less brought us then towards the fact that, okay, this is actually not explained through the gain medium. So Wang Chou also published one paper regarding this theory, this multimode theory. And at the beginning, it was also a little bit difficult for us to follow and to understand 100% what was happening there. So basically, the idea is that, of course, the inside of the cavity, you have one mode that is the very, very much pronounced and is more or less, very, or not verified, so being according to the standing wave approximation that you have inside the cavity. So fulfilling so fulfilling the terms of lasing modes. But what's happening also outside of the cavity is that you have still a more or less continuum of modes that still exist in there in the free space. These modes can basically interact in this free space and they couple to each other, and that way they start pulling they start pulling towards the central mode, which gives then rising to this Gaussian part. This is performed also basically through the medium non-linearities in the cavity as well. In this sense, I'm not 100% in the case of explaining everything perfect, but this is the assumption then that what we derive also through the equations of motion for the intensities of these modes is that they couple to each other and they start pulling above the lasing threshold towards the central mode, giving an arising to the more Gaussian profile then.
Would this be a peculiarity of the geometry that you're using, this encapsulated thing? Because I should think in some sense, any output coupler would give that kind of effect. I forget whether you said what the Q factor of these cavities was, but
the Q factor of this cavity I didn't say, but it's not something super big because you have the metal in there, you have the silver, so it's at about 2000. Okay. But we have also seen that in dielectric micropillars in a sense, because afterwards we're starting also relooking at how there are a lot of fits, and we have also seen that in dielectric.
You see that in dielectric micropillars. Okay, then in some sense that's more convincing, because that means that the output coupler actually is playing the function in any case, because otherwise you would have understood it. Yeah, okay, fine, thanks.
Yeah.
Thank you. I also have a question regarding the G2 measurements, where you found first from the experiments that it increases slightly above 1 at tau equals 0, right? And then when you use the Siegert relation, then you kind of get this what you have here on the right exactly. So I'm not familiar with this relation before. So can you explain a little bit about its physical origin and like where does it come from and what determines the value of A?
Yeah. So basically, if you forget the value of A and you just set it equal to 1, this is what Sigurd at some point derived from the idea of, is there a correlation of the G1 and G2? So is there like a connection between the first order correlation and second order correlation? And this is something that he derived for a chaotic system of an ensemble of many emitters, so thermal emitters in the sense as well. So this is a relation that's well known, that is very, very valid for the thermal regimes, so to say, where you have more or less a classical system in a sense. But of course, this is not possible if this is not something that's very, very much valid for the lasing, for the Poissonian statistics. And this is also shown in the paper of Monty Drexler, where they investigated what kind of validity does this Sigurd relation has. And in the sense when you have a lot of emitters and then you have a lot of dephasing, for example, in the case where you have a quantum world, then you have many emitters, so you have very quick dephasing, then the validity of this extended Sigurd relation is good. What you do in this sense is that you just add this parameter A in front, because if you set it equal to 0, then you would have G2 is equal to 1, which is the lasing. It's the one side, so to say, of the spectrum, the one G2 that we want to produce through the Sigurd relation, and the other one for the A equal to 1 would be the thermal regime. It would be 1 plus 1, then it would be G2 equal to 2. So we want to see what's happening in between. And this has provided a very good solution, I think, in the past 10 years when people started to try to deconvolute this raw values due to the low resolution of our setups.
So in the end, what determines which value you choose for the A? Like how does it?
This is practically being calculated through the fact that if you take the integral of those both sides, then it doesn't matter if the function is convoluted or deconvoluted. And you can relate A to the area underneath the surface of the G2 peak and the coherence time. And through that, you can calculate how big is A, in the sense of what kind of pump power do I have, what kind of surface area and coherence times do I have, and that gives you basically this A value that you need to deconvolute the values. Yeah.
Okay, thanks a lot. Do we have any further question? I don't see any, so let's thank Aris again.
Thank you very much.
And let's move on to the last speaker of today, who is Shihao Ding from Paris. You can now share the screen.
Okay, thank you. Can you hear me? How about the slides? Can you see the slides?
Yeah.
Okay.
So now we see the PowerPoint.
Okay.
Okay, go ahead, please.
Okay, thanks for introducing me. My name is Shihao Ding from the TechCom Paris, and today I will present some recent results about the multidynamics in the silicon-based quantum dot lasers through the optoelectronic feedback. And we know there are some features of the silicon-based quantum laser, like the high defect tolerance and the low threshold current, and advantages than the other quantum wheel lasers. And especially for the optical feedback, in our group, we have some papers to explain how the QD lasers show the strong optical feedback tolerance. We could see when you apply the optical feedback, the transmission properties doesn't change much, and the eye diagram open very wide and very clear. And also when you apply the optical feedback on the quantum dot modular laser, the RF noise will be reduced. So the silicon-based quantum dot laser shows very high performance. And we are thinking about how to extend the applications of the quantum dot lasers. And we want to using some nonlinear dynamics to do some applications like the microwave generation and optical chaos cryptography, and a very hot topic, the resolve computing like this. So by using the semiconductor laser, we could apply the optical feedback or optical injection on the laser to generate the different dynamics to do the applications. But for the quantum dot laser, we said before, the quantum dot laser are very insensitive to the optical feedback. So that is not a very good way to generate the nonlinear dynamics. So second, we could consider optical injection, but if you pumped a very high injection power to the laser, could damage the quantum dot laser. And also another optical source is not an efficient way to integration on the silicon. So we need to think about another way to do the dynamics generation. So we find the optoelectronic feedback is a very efficient way to integration and to generate the nonlinear dynamics. It's a loop to contain the optical path and the electrical circuit. You could feedback the electrical signal to the modulator, like the MDM phase modulator like this. And you can also directly feedback to the laser by using the nonlinearity of the laser to generate different dynamics. So by using the different dynamics, you could apply it on the optical sensor, like you could detect the strain of the fiber, or you could generate a chaos to do the optical chaos cryptography and also the optical computing. Like recently, the Microsoft has some setup to do this optical computing. And so in our research, I will show you what kind of lasers we use and how we build a setup about the optoelectronic feedback, and what kind of nonlinear dynamics we find. And we also have a model to explain why we can find this dynamics. So here we use the silicon-based quantum dot laser from the John Bars in UCSB. The laser has a FP cavity, and the active region has 5 quantum dot layers with a p-dot barrier. And also the facet has a 60% and 99% reflectivity. So with this structure, the laser shows very high output power and low threshold current at different temperatures. And we just put the laser in the optoelectronic feedback loop, and output light will pass through an isolator in case of any optical feedback, and then to the SOA to enhance the optical path, and to the electrical path to a PD and amplifier and the attenuator to adjust the different feedback strengths, and finally to bias T to feedback to the laser. And all the electrical components has the bandwidth, all the bandwidth we need to consider, because at the last we need use the bandwidth to do the simulation. And here by using the setup, we could record the electrical spectrum at different temperature with the feedback strengths. We could see a 0.5 gigahertz oscillation here, and the oscillation will be more prominent and extended on a large frequency region at a high temperature. And also when the feedbacks increase, the low frequency noise will gradually intensify, especially at the high temperatures. But from the electrical spectrum, we cannot clearly see what kind of dynamics we find. So we need to use the oscilloscope to record the time phases. And we also record different time traces at different temperature and by varying the feedback strengths. You could see that at room temperature, the QD laser could change from a sine wave to, let's say, square wave, and to a square wave and finally to get the fast and slow oscillations. And at the high temperature, the QD laser doesn't. We didn't see the sine wave just changing from stable to the quadratic square wave to the square wave and follows fast and slow oscillations. And also, we could see 2 nanoseconds periodic time in the sine wave and the quadratic square wave. That is because of the high cutoff frequency, about half gigahertz in the system. And also, we could see a 20 microsecond periodic. It comes from the low cutoff frequency, like 50 kilohertz in the from the bandwidth in the electrical component. And also, we have a loop. So there is a square wave with 250 nanoseconds. It just comes from the OEF loop. And also, we could see when you apply the OEF at the room temperature, at low temperature, the square wave shows more clear and more better than the high temperature. And we could see the QD laser can generate rich dynamics with the OEF loop. So we want to compare with the quantum wave laser. So we apply the same setup as shown in the left 3 figures. We could see we cannot generate the square wave and fast and slow oscillations, just the stable and sine wave or triangle. And we want to see if we insert another electrical amplifier, how the quantum wave laser changed. We find the laser shows the fast and slow oscillations here. So here we could see the quantum dot laser are more sensitive to the optoelectronic feedback than the quantum wave laser. So we want to build a model to explain why we can find the different dynamics in the quantum dot laser with the OEF loop. Like some people using the Ray equation method to do the simulation, they find the same phenomenon by using the Ray equation, but they cannot find the square wave and the fast and slow oscillation, just like some period oscillation and chaos like this. So when people find the square wave by using the OEF loop, they think about how to improve the Ray equation method. So they insert another 2 equations about the high pass filter and low pass filter. So in this model, if you have many electrical components in this loop, like 4 and 5 electrical components, you need 8 and 10 equations to do the simulation. So it's the computation is very huge. So it's not a very efficient way to do this simulation. So we try to find another way to build up our model. Like we know the Ikeda system is also a loop system. They consider 4 elements in this loop, like the nonlinearity function, and delay time, and bandpass filter, and also the gain in the loop. The most important thing, we need to find the nonlinearity function in this loop. So when people do this simulation, when they apply the OEF on the modulator, they consider the nonlinear function as from the modulator MDM. So they use the cosine curves to do as a nonlinearity function. By this way, they could find like the square wave fast and slow oscillations. But in our system, we just feedback the electrical signal directly to the laser. So people also do this simulation with the non-unitary function. They consider the non-unitary function between the laser and the photon detector. So they can find the piecewise linear function in this system. But in this paper, they just use a quantum wave laser, and so they can just see some periodic oscillation and like a chaos-like oscillation. So maybe in our system, we use the quantum laser. It could be have a more complex nonlinear function. So we measure the nonlinear function of the QD laser and QW laser. And just from the output power and the response curves of the PD, we can extract the nonlinear function. So using this model, we could get the bifurcation diagram. We could see the QD laser has more complex dynamics when you increase the feedback strength. But for the quantum wave laser, it can just see shows the stable or some simple oscillations. So from the mapping with the experimental results, we can also see the same situation. The quantum dot laser shows more abundant dynamics. So we could see from the simulation and experimental way, we could also see we proved the QD laser has more sensitive to the optoelectronic feedback. So in our system, we could see with our model, we could see the same square wave and the faster slow oscillation with the same periodic and same shape. So there's no problem when we using the ICADA system. Finally, we could see the QD laser can generate different dynamics like the sine wave, square wave, or the fast and slow oscillation. And other people say that is the breezer. And also the square wave region can be bordered when the temperature is low. That is beneficial for the optical clock. And also by comparing with the quantum wave laser, the QD laser shows very strong sensitive to the optoelectronic feedback. And we use the ICADA model confirm the above phenomena and obtain the time traces consistent with the experiment results. So maybe in the future, we can find another very complex nonlinearity function, like if the QD laser has the excited state emission, the nonlinear function will be more complex. That is where maybe it can be bring more dynamics with the optoelectronic feedback. So thank you.
Thanks a lot, Stefan. Do we have any questions from the audience?
Yeah, if I may, I do have a question because I thought at first you were saying that the quantum dot at the beginning of your talk.
Okay.
You mentioned the fact that the quantum dots are less sensitive to feedback.
Yes.
And I assume you mean optical feedback, right?
Yes, it's optical feedback.
I am trying to understand the physical origin of the reason why, and I haven't understood it from your modeling, of the reason why the optoelectronic would give you a much more complicated dynamics. I see the way you get to the model, but I don't quite understand the physics. Okay. Can you help me explain that?
Yes, yeah. Actually, I said before, the most important thing is the nonlinearity function in the model. So you could see like if you use MDM, why they use MDM? Because the MDM can bring more nonlinearity in this system. So they could see a very sine wave-like function here. And in our model, in the QD lasers, if the QD laser has some, because the QD laser has more complex energy levels, like has excited states are resolve layers in this energy level. So the carriers transfer process more complex. We could see the carrier process from the PI curve. If you have the excited states, the PI has more steps here. You know this. If the QD laser has excited states, the PI has like 2 steps or 3 steps here. So in the PI will bring more complex nonlinearity in this nonlinear function. And also, if you use the, but it's not a problem in this system because we use the same PD here. If the PD has more nonlinearity, it can also bring the saturation nonlinearity here. So the most important thing and most the physics is the nonlinearity of your QD laser or QWs. The QD laser has more complex energy carrier energy level, so it can be bring more complex nonlinearity. And also for the QD laser, it has a high gain saturation compression factor. So the QD laser can saturate it more fast. It can be also bring some nonlinearity at high voltage or high current.
Okay. What is the level scheme of the QD lasers that you are using?
Sorry?
What is the level scheme of the lasers, of the quantum dot lasers you're using? How many levels are involved? Is there a wetting? Okay, but those are the layers. They're not the
yes.
not the levels. I'm talking about the energy levels.
Energy level.
It's what I understand. I thought you meant. I thought you meant there were the energy levels that had the complex structure. That's what I understood from you.
Because it's 1.3 micron wavelength, so it might be 0.95 EV like this.
Yeah, something like that. That's fine.
Yes, yeah.
But
and for
I understood you're saying that there was a multi-step process in order to get to the transition levels.
Yes, but in this model, we cannot consider the structure of the energy structure of the laser. We just input the nonlinearity function, and but in this re-equation, maybe they can bring some. They can insert some energy structure, maybe, but they cannot find the square wave and other dynamics. So we need to consider in the future to mix.
Thank you.
Okay.
Okay. So let's thank Shihao and the previous speakers again. And I believe it's the time to close the session, and we will then meet again tomorrow.
Yeah. Thank you very much. Thanks, Santi.
Thank you.
Thank you. Have a nice evening.
Bye. Yeah, bye.